Professor Lynn taught at Yale, Columbia, UCLA, and the University of Illinois at Chicago. His writing is well known abroad, and among his books are Animate Form from the Princeton Architectural Press, and Folds, Bodies, and Blobs, collected essays published by Les Lettres Volées. He also serves on the editorial board of Any magazine since its inception. Professor Lynn works collaboratively with a variety of architects on a range of projects, including the Cincinnati Country Day School, the vision plan for Rutgers University, the Ark of the World Museum, and the recently completed Korean Presbyterian Church in New York. There he worked with Garofalo Architects and Michael McInturf. That's the project that many of you have probably seen. It has received a great amount of attention in the recent press. Professor Lynn's research activities deal with the use of advanced computer software for the design and documentation of buildings, and with the use of computer numerically controlled machines for the fabrication of building components and architectural models. Recently, I was privileged to see in his studio a computer-controlled milling machine produce a negative of a varied vaulted space on which they were then working. Professor Lynn will speak to us about the differential calculus of the sketch. Please join me in welcoming Greg Lynn.
Well, talk about a tough act to follow. I thought what I would do is lay out very quickly some thoughts about the sketch in relation to I'm going to say new geometries that architects are using, but when I say new, I mean invented 300 years ago. But first, I'd want to just clarify what I understand the sketch to be. I think I can come up with two interpretations of what a sketch might be. One would consider the sketch as a diagram. And when you think of the sketch as a diagram, you think about something to which you can devolve your project, or to some primitive form or primary form which regulates the design process. I think this model of the sketch as diagram would lead towards a mathematics of whole numbers and towards a mathematics of algebra and fixed points in space, because you need those fixed coordinates to regulate an architectural design. I think the other model of the sketch, and we could probably come up with hundreds of terms for this, but I'd call it the sketch as the plexus, which is the notion of the sketch in a developmental and evolutionary sense. And I use this term plexus because it connotes a network of curves or a network of shaped elements which define a relative center, but which have no exact point of origin or no exact figure. And so for me, the sketch is more evocative as this model of the plexus, or the network of curved lines which define a relative whole or a relative center, because it engages the mathematics of calculus, and it engages a geometry of curves and splines. Now, to just quickly state the question that Irving posed to me when he invited me to the conference, he said, well, Greg, I'm hoping you can talk about how you can sketch with a computer. And to me, that's really the way I think about the computer, is primarily as a sketching tool, and it's a tool which lets me sketch using the mathematics of calculus rather than the mathematics of fixed points like you'd use with a drafting tool such as a parallel bar or a compass or something like that. So when we're drawing with the computer, we're drawing elements which are called splines, which probably not everyone's familiar with, but a spline is a type of geometry which is based on a Bezier curve, where Bezier tried to develop the mathematics for a string with weights hanging along it, and the string would take a particular shape based on the location and weight of the components that were hanging it. So a spline is a geometric primitive that you draw, which is a curve. Even if you have a straight one, it's actually a curve with just equal weights. And you move points, and a stream of points falls in between them, so that your shapes and your curves don't really have points in space. What they do is they hang through a sequence of points and are calculated based on all of the variables interacting with each other to generate a curve. So you get a kind of holism or a kind of continuity, but it's a continuity that's not based on a reduction to points or a reduction to a primitive form. Instead, it's a highly relative kind of geometry you're using. And these images on the videotape, I just thought I would show for a second. This is the way we work. This was for a study for a line of houses. A few years ago, I was at a conference sponsored by Volvo where they were trying to come up with a design technique for infinitely variable cars in terms of their interior and exterior dimensions. And they decided to invite architects because they thought architects would be the only people that could engineer a system with enough flexibility that they wouldn't have to re-engineer every single car. So it got me thinking about the modern house and the logic of a non-modular, non-standard system of construction. So we tried to come up with a volume for a house where we could fix the number of components and fix the system of construction and infinitely vary the shape, always having the same number of elements. And it actually brought us back to Alberti's dictum about symmetry and proportion, where we tried to have a house to which no part could be added or subtracted without violating the harmony of the whole. But in this case, there was no primitive geometry regulating that harmony. It was a non-whole number system of proportion. So we came up with a set of limits and then could vary the organizing shape within those limits and then spit off all of the components. Okay, so I'm going to stop that. If I could get the 2 slides. So I'm going to just skim across a few projects, hopefully to pull out the qualities of sketching with the computer that relate to each one. The first 2 projects I wanted to show, first in terms of the computer sketches that we use to organize them, but then I want to show a kind of proportion and tectonic, let's say, which is literally calculus-based. This is a sketch we did for the church in Queens, which Hank mentioned. And for this project, we built a new sanctuary for 2,500 people on top of a factory. And so we had to think about what the ground was, which was an existing building 2 stories in the air. We tried to model a sanctuary space that could nest on top of it. So we built, instead of a church typology, we took the elements of the church, being the altar, different organizational plans for the pews and the choir. We gave each one of those things a primitive, and then we networked the primitives together so that whenever they would come close to one another, they would start to stick together and form a whole. And I mean, just so you can see how these things are working, each element has a sphere of influence, and you can see that this piece is starting to get tugged towards this piece, and similarly this is getting tugged. As you increase the force of the traction, they begin to stick together. But what it gives us was a sanctuary space which was whole and continuous, but every piece of it was simultaneously being defined by every piece we were modeling it with. So if we ended up moving one little corner of it or tuning it up, the whole shape would change in continuity. And that's the calculus quality of the modeling, that this was a relative space. It wasn't based on any pure form or any pure type. It was relatively defined by the interaction of these components we selected. And in the construction of the church, you'll see that those geometries were transformed into linear and curved architectural components, each one of which was a subtly different dimension. And in terms of construction, we first made some mistakes and regularized our column grid, but instead of making these equally distant in plan, we looked at the topology of the surface and could apply 22-foot increments on each panel in their plane. And we could work with both standardized and custom components. Standardized and custom components to generate the tectonics of the building. Now, what's like calculus in this kind of an architecture is that every single element is a different dimension because they're not based on a standard span or a standard form, but each one of the elements is related rhythmically one to the next in a sequence because they're all falling off of the same variables. So that what you get is a new kind of proportion or a new kind of harmony, let's say, which is primarily rhythmic, rather than being based on a standardized syncopation to which you see a variation. Here it's pure variation, but it's variation in a continuous sequence. And again, you can see the structural framing of those elements. And here the interior similarly. You can see how you get these rhythmic sequences of components. So the first concept of working with a computer, which is working off of mathematics of calculus rather than algebra, is you lose whole numbers, you lose standardized dimension, and in place of that, I mean, it's not really a loss, but you advance that logic, and in place of it, you get rhythmic sequences based on interacting variables or interacting components. And you can define the envelope of those limits so that you know within that envelope all of your components will be of a certain maximum or minimum, but everyone will be different. And I think the most important thing is they'll be different in a pattern rather than just being varied for the sake of being varied. The variation has a mathematical logic and sequence to it. A similar example of that is a project we're doing renovating a kilometer-long housing block outside of Amsterdam in the Bijlmer. And the building's poured in place concrete, which we really can't touch. So we're reorganizing the building by clipping a new system of public space and circulation along the facade, and then reorganizing all of the parking and access to the project. But I'm showing you this so you get a sense of this monotonous kilometer-long repetition of housing, of apartments, to which we add a new system of organization. So you see escalators and stairs here, and wherever we add those circulation systems, we also add a combination of glass and plastic skin, which look like these kind of petals, which get wider wherever they conceal public spaces and circulation. So that in the, in this rendering of what the project looks like, we get a high degree of modernist repetition of these components, and every element is more or less the same as every other element in the system, but no two are ever alike, but their neighbors are always similar to one another. So that this kind of an organic logic of a component being based on the relationship to its neighbors, where every component is unique, but they're highly repetitious and iterative, that's really a mathematical and geometric principle that could be generalized. And when we're sketching, we're sketching trying to achieve these kinds of effects. And although, I spend quite a bit of time drawing, it's really impossible to draw this kind of complexity without a computer because you really need the mathematics behind it. And I find it more and more difficult to sketch these schemes because it's, to me, easier to sketch a kind of, well, a square like Lucan or a primitive which is algebraic than it is to sketch a primitive which is calculus-based. Okay, and these are some images of those fins, how they clip onto the existing factory. So the house which I showed you the video of first was defined with, I think, 64 control points, all of which could be varied within a certain limit, and each of which controlled a much more complex set of surfaces. So we built this skin out of a little bit over 2,000 components, but we could always manage each one of those 2,000 components with those 64 control points. So we had the liberty as designers to modify the controlling geometry and then through the computer break those 2,000 panels into components and template them out so we could cut them with robotic tools in 2 dimensions. So here you see 2 variations of the house. And all of these systems are completely automated. So we do this transformation one time, then we can literally take any form we want and automatically do the working drawings for it, basically. Or here we break the surface into curved plates, which are then manufactured with a robotic mill and cast in plastic and reassembled. And these are some images. We took 6 of the houses and worked them out in terms of structure and cladding. And you can see here the unfolded templates of all of the cladding systems in metal and all of the glass infill in between. And this is just to show you the difference. This is one example of the house. This is a second example. So same number of pieces. We don't ever add or subtract anything, but every piece is slightly different within a very subtle limit. But by adding up a lot of minute changes, you can get very major building scale features. A kind of spin-off of that research was a commission to do a line of showrooms for a Swedish housewares company called prettygoodlife.com. And I mean, to testify to the commercial value of doing research, they called and said, we're looking for a series of showrooms that are blobs which can be adapted to different situations around the world. And we said, well, that's exactly what our office does. So we started off with a uniform identity for them for every showroom, that it would come from the same geometric primitive. And then we showed first how we could change kind of typologically the features of any one of those primitives, which you see here we did 5 variations because they started off with 5 showrooms. Then we showed how we could fit those different types to various kinds of urban situations. So an infill storefront in a, say, a shopping mall or a galleria versus a storefront on a street, etc. We almost bake them like bread to fit into the confines of different situations. And we then looked at developing those surfaces geometrically and preparing them for a computer tool so that we could build them using the same technology anywhere. And what I found, and I know that a couple of these companies, Frank pioneered using them, the automobile prototypers in California, there are 4 different firms that make automobile prototypes, which are body-formed and interior blocks of foam which roll around for car shows. They don't actually drive, but they have the skin and the structure and the interior of a car. And the per square foot cost of building one of those for Audi last month was $400 a square foot. So the square foot cost of building one-of-a-kind working cars is basically the same square foot cost of a kind of high-end residential house or a high-end interior. So we use these automobile prototypers to make all the components, and in Sweden we called up the prototypers that work for Volvo and Saab and just sent them files over the internet, and they built the interior of our showroom using these cutting tools. So one of the things that we found, and this is a piece of that interior, is that rather than make a building that looked like a computer rendering, we wanted to use the tool and its artifacting to produce a new kind of materiality. So these ridges that look like kind of corduroy are the artifact of the bit which is used to cut the wood. And we found that we needed to program the paths for this tool so that we could always get our patterning to align. And we started to think about the artifact of the tool as actually a design technique, and started to basically sketch what the articulation of these surfaces would be based on the control of this bit. So these bumps that you see that we put on it and those paths, in the finished interior, were very much part of the aesthetic and the materiality of the surface. So instead of trying to make a slick, reflective computer image in built form, we're really trying to use the tools to generate new kinds of articulation and even a kind of ornament. And you'll see the last thing I'll show you is a kind of much more developed version of that. This is the kind of my newest obsession, which is a figure called a bleb. And it's all industrial designers, this is the bane of their existence. The problem is when you use these spline curves, whenever you have a curve which has convexity or concavity, when you offset the curve to give it material thickness, the curve intersects itself. So you can see this fold, when offset with this much material thickness, first develops a single intersection like this, and eventually folds through itself 2 times and generates these geometric problems, basically, of a surface which intersects itself. And all of our software has tools which clip these things away and they disappear, but it always screws up the rigor of our surfaces. So a year ago, I started turning off this automatic procedure, and we started using these captured spaces as an architectural scale spatial device. So one of the first things we did is we're doing large scale, I hate to say art objects, but art objects for Max Protesh, who has a gallery in New York, where we're doing additions of lighting fixtures, additions of floor elements, additions of wall dividers, where we'll build 10 variations of a very similar piece. And these are diagrams for a skylight, the first one we're building right now. And we went with single, double, and triple folds and started to combine these things into different patterns. And you can see here, 3 of those folds merging with 1 along this axis, 3 merging with 2 in that axis. We came up with a kind of catalog of all of the geometrical possibilities we could think of those folded components, and then started to select and redesign the ones that were giving us the most promising architectural features. So these are the 10 that we're building for the skylight systems. And each of the dark components are where these elements fold through themselves. And this is a photograph of a scale model. These will be about 10 feet by 11 feet square. And this is a model of the formwork that will cast the plastic on. So you can see the rippling and ridging becomes part of the surface effect. And it has a really strong optical quality on the clear material when we cast it. And here we have to break these geometries into components. So we'll cast first one large piece, and then we'll cast these pieces individually out of two components. So we'll build these out of sheets, and the way we subdivide them is really based on the manufacturing technology. Then this same technique we used for a proposal for a new museum in Chelsea that I did with David Childs and Roger Duffy of Skidmore, Owings and Merrill. We decided to team up. I'd never done a vertical project, and they're the masters of towers. And we thought it was a good opportunity to apply some of these surface modeling technologies to the design of a curtain wall. So for this project, this is about 30 stories high, and it's right on the Hudson River, we decided to model the building as a surface which folded around, and we decided to give the building its identity by folding the curtain wall skin out onto the street. So this is a primitive version of what we started with these spline curves. And you'll see progressively this box is a detail of this form right here. We took the geometry of the surface and began to dent it, and then loop it and fold it through itself, so that the exhibition spaces, you see these blebs forming, so that the exhibition spaces take the vertical mullions of the curtain wall and fold them out and literally turn the surface of the building inside out, so that what was the inside surface of the museum gets folded around outside to make these volumes, and these become occupiable spaces for special installations where you get total surface presentation. So they're like immersive rooms adjacent to more banal gallery spaces. And this is on 21st Street. And the entry are these folds here. There's one piece where we take the street and fold it into the building, which I think you'll see here. This is a structural diagram of how we build it with these structural mullions that hang on the skin. You can see here we fold the street into the building to make a large auditorium and event space. So the kind of geometric problem and the ability to sketch it with the computer became the generative tool for rethinking the building facade. And these are images of it. The top 10 stories of this are non-occupiable, but we found out this museum wants to use the top 4 floors of the museum to lease office space to kind of internet startups. And it's worth about $32 a square foot right now, probably less every day. But we found out the surface of the building is worth $23 a square foot as an advertising surface, and that we could actually build this zone, which is pretty unusable by the time you put a core in it, and project images on it, almost like the kinds of curtain walls that are in Times Square, and that the museum could start to have a presence on the city skyline using the upper portion of the building for digital display and presentation, so that there's this kind of exhibition space on the surface, and then there are these folded surfaces which make for exhibition spaces on the street. These are views of the interior looking out into these folded volumes on the facade. Okay, finally, the last thing I wanted to show you is the third collaboration I've done with a painter named Fabian Marcaccio. And Fabian and I have been trying to find a way to work architecturally and with painting where both of us remain experts in our own fields, but where we start to collaborate in terms of the form and surface of the installations. So this is a detail of one of the painting that we started this particular collaboration with, and we wanted to build a three-dimensional painting, and at the same time we wanted to build a painted architectural volume. So I was in charge of constructing the envelope for this painting and texturing it. Fabian was responsible for the figure, the color, and the paint effects that would go onto this. So what we did is we built a sketching machine in the computer which worked like these diagrammatic brushstrokes of Fabian's, and we spent 6 months kind of going back and forth thinking about the form of this enclosure in the gallery space. And this is a detail of one of those models. This is about 100 feet long, as the snake slithers. It's in the Wexner Center in Columbus, Ohio. It just came down. But it was meant to be like a sketch of one of Fabian's brushstrokes at the large scale of the museum. And we wanted it to work with the gallery so that as you came up to the top floor gallery, you'd see this thing kind of looming. But then once you came into the gallery, you'd see the scale of it and really feel kind of captured along the walls. And as you walked around it, you'd feel pressed against the walls. So these are some of the studies. I mean, you'll see fairly major variations in the form between each one of these studies. This is an example of 4. We would send these to Fabian in New York. He would overpaint on them, send them back, and we'd reconfigure them kind of back and forth. And in the end, we settled on this particular volume, and Fabian produced a special digital painting that was about, again, 100 feet long that we could map onto this surface. So we defined the figure of this kind of three-dimensional paint trail. We then mapped the painting area onto it and started to think about materials, and we wanted it to be translucent plastic so that you would sometimes read the form in plastic and other times read the painting like a kind of like a Chinese lamp or like a painted illuminated lamp. Now, because of that project in Stockholm, I wanted to get the texture of the painting onto the form of the surface. So we first took this form and broke it up into little panels. You can see it's like filleting a fish. We skinned each one of them into panels that would fit onto a 5-foot wide machine, and then we broke them into panels so that we could mill them out of a 1-foot depth. And we then gave Fabian this unfolded pattern, and to his horror, he had to take this 100-foot long painting and anamorphically map each one of his painting panels to fit onto each one of our pork chop shapes so that when we put all of these pieces together, his image would be continuous. So this was technically a kind of the anamorphosis to get this flat image to these complex curves was one of the main technical achievements of the project. Then you can see his painting broken up into all of its respective pieces for the panels. Then these are the panels nested onto 4-foot by 8-foot sheets that we cut with a computer-controlled mill. Then before we, with maybe a month to go on the project, we had the idea of taking some details of his painting and mapping them on the form at key locations and turning that pictorial image into relief on the surface of the form. So that instead of being this slick, smooth form, we got these 3-dimensional kind of impasto brush strokes all across it that were maybe 3 inches in relief. So that the pictorial color image got mapped onto them, but also 3-dimensional surface pattern got mapped onto them. And then when we took this into the computer to generate the cutting paths, we could have the drill basically move around on the surface like a paintbrush so that it moved with the same pattern as Fabian's brush, just digitally translated into a machine code. So I think there are some details. I mean, you can see these vertical ridges in the plastic are from the tool but these horizontal strokes that unify the panels and make these large-scale brush strokes on it were where that tool jumped and bumped around and started to move like a paintbrush. So we were really trying to use a piece of computer-controlled technology, with a stroke, which was the stroke of an author rather than the stroke of a machine code. And these are just various images. This is probably, where these three-dimensional strokes worked with painting. It's probably one of the more successful areas where all those things came together. And then Fabian came back in with paint and silicon, which is his kind of signature, and started to pull the printed, these were all digitally printed panels of plastic that we formed. He would start to pull those pictorial elements out into silicon back again. And so he went over and spent a week just painting the three-dimensional painting again. Yeah, there's a perfect example of it. And the apertures that we put in it, these shreds, came from the house research where instead of punching windows in it, we really tried to use the surface topology and just expand the splines to make openings, which we cut into it. And at one point, you could get inside and walk around. Right there is where you can walk into it. And we put the painting on the inside face so that it would be a little bit opalescent when we lit it from the outside, but then it would be very intense with paintings on the interior. And that's it. Thanks.